know the problems involved, especially in converting the IGS files into SLDPRT. Most of the time, SolidWorks does a pretty neat job in converting it and giving a much better part file. But there are these instances where you always get into some problems where some of the surfaces are not good enough for machining. They could be good enough visually, but they're not good enough for machining, which then SolidWorks gives up some tools which you can use to correct those surfaces. Sometimes you will see the patches itself are disappeared. You need to fix those patches inside SolidWorks. My experience says that the step is much more cleaner way of transferring data between systems, two different systems. And the most cleanest one that I've seen is transferring data using Parasolid, because SolidWorks works on the Parasolid engine, so it makes much more easier the translation between System A to SolidWorks or System B to SolidWorks. So if you're going to get a part from your own vendor, your own customer, make sure that it's in Parasolid. That should be your first choice. Then step, and if there's nothing, then IGS. Of course, you can import directly the files from ProEngineer. You can import directly files from Unigraphics, also from Inventor. But the best possible path that I've seen so far is to go through Parasolid or step. So once you have the part inside, if it's a Parasolid, 99.9% the file will be pretty clean. It's that 0.1% where you'll have to fix some of those patchy surfaces or missing areas if they are missing or if they are not perfect. The other very important thing when you're machining large parts is to ignore or to close up those small areas. What do I mean by small areas? Small areas means ribs, small holes. I call them speed breakers. It's essential that these things are closed up, because most of the times these small areas are always machined later, or they are just eroded using a spark erosion or a copper electrode or the EDM process. So in milling, we need to patch them out. The other important thing, apart from handling of the geometry or cleaning up the geometry, is setting your computer itself to work with large parts. If you've not been working with large parts, chances are that these settings are on their default. And when you use these default settings and go for handling of large parts, there's every chance that your system will slow down, sometimes crash, because these systems need to be tweaked up for handling up of large parts. Apart from computer settings themselves, what you need to also understand is the tolerances that you use for calculating tool parts are not going to be similar to what you have been doing earlier. Let's say you have been doing production parts, and suddenly now you're asked to work with a big die. The kind of tolerances that you're using with production parts are not going to be the same what you're going to use with a die mold component. Yeah, they're going to be different. For roughing, they're going to be different. For finishing, they're going to be different. So the tool part tolerance need to be set properly, first of all, to bring down the calculation time, and also to get a much better machining speed on the machine itself. Because the tighter you make the tolerance, you're going to get more number of points, and that's going to bring down the machining time itself. In our next webinar, in next week, because it's a completely different chapter, I'll also share with you the simulation settings that need to be done for extremely fast tool part simulation on very large parts, or where you have tool parts with millions of lines of code, how quickly you can run the simulation. So that will be a completely different webinar, which we're going to do next week. Also, we'll also show you some internal tweaks or some internal settings that need to be changed slightly for better handling of large parts. So this is a gist of machining the large mold insert, or this is the way you can actually achieve machining of large parts, apart from the tool part strategy itself, which we are going to see in the part itself. These are some background work that need to be done so that you can easily handle and machine large parts. Right, let's run through the first most important thing before we even open up the software, and that's our systems. If you have been machining using, or if you're doing the machining on production parts, probably you would have taken the base system of a computer and things would be progressing nicely. But when you move to a much complex part, much bigger part, with thousands of surfaces inside it, which is going to generate several 100,000 lines of code, then you better have a much better system on which you're going to have SolidCAM. So the first important thing is the processor itself. Everyone today has an iCore 7. In some workstations, like a Dell workstation or an HP workstation, you also have the Xeon processor. So it's a toss-up between a Core i7 or a Xeon. If it's a branded workstation, then you'll never get Core i7 on it. You'll always get a Xeon processor. The memory is very important here. If you're doing production parts, or if you're doing mill turn or small aerospace components, 8 GB of memory is pretty good enough. But when you're doing mold and die components, large mold inserts or large sheet metal dies, then 8 GB of memory is not enough. You need a much better memory. You need about 16 GB of memory. Also, what is more important is what kind of a graphic card you're using. I have customers out here who assemble systems on their own, and they put a GeForce card. A GeForce card basically is a gaming card which works on frames per second. And this doesn't give you the kind of quality that you actually need to process graphics for such large parts. You'll also see that when you're rotating large parts, especially when simulating it, you'll see that the performance of the graphics of GeForce is very sluggish. In such cases, you have to have a Quadro card, which is basically a pixel-based card with a 2 GB of dedicated video RAM. As far as the storage goes, I recommend that you split the storage into something primary and a secondary storage. A primary storage basically will be an SSD, which has got much faster accessibility. Why that accessibility is needed, we'll look into our next slide. And then you need a storage where you move data between what is being calculated and what has already been calculated. For example, you have two projects. You have done one project, it's finished, move it to the secondary storage, and bring the second part from the secondary storage to the primary storage, and run all the calculations on the primary storage, which is the SSD. And we do suggest using Windows 7 Professional with SP1. I know that there are much better OS that is available now. That's Windows 8.1, but my experience has been pretty good with Windows 7, although it's a old OS, but it works rock solid. Right, now let's go and understand why do we need the 250 GB primary SSD. The most important thing when you're doing large parts is the virtual memory settings. I'm not very sure how many of you would have paid attention to this particular setting on your computer. Basically, virtual memory is pretty useful when you're doing large parts, because your memory is already cluttered by several programs that are running, and what the software will do is it will only take the portion that needs to be calculated into the RAM, and it will push the other remaining data onto your virtual memory. So having a good amount of virtual memory will ease the load on the system. So what I suggest, first of all, I do not suggest a system managed size. This generally doesn't work. It's very important to understand there is some recommendation that Windows comes up with, and you need to exceed that recommendation. So if you're having a 16 gigabyte memory on your system, I would suggest a custom size with an initial size of 2 times the memory and a maximum of 2.5 times of the memory. The general nomenclature is about 1.5 times of the memory to 2 times, but I go with 2 times and 2.5 times. So you actually exceed the recommended allocation. Okay. In this case, the recommended was 24 gigabytes. I've given it 32, so I've given it enough to work with. All right, so the virtual memory must be set on your SSD. Why? Because it should not happen that your memory, which has got the fastest of the speed because it's sitting on the motherboard, waits for your virtual memory to transfer the data. If your hard disk is slow, let's say you're using just a 5,400 RPM hard disk, it's pretty slow. So your memory will always wait for the hard disk to dump the data onto the memory or vice versa. So it's very important to have your virtual memory on your primary partition itself, which is, in our case, if you're using an SSD, it will be on the SSD drive. So the exchange of data will be very fast. So you'll not see the system lagging down when it's doing the calculation. Right, so it's very important. If you have not done the setting, even for your other purposes, if you're doing even a medium complex part, I would suggest to go and change this. Not by yourself, of course. This is something that needs to be done by your administrator. Right, so we have seen a bit of system settings. We also will now understand, apart from the system, what do we need to do inside the software itself when you're handling large parts. Okay. First of all, you have to understand that the toolpath tolerances greatly influence the calculation time. It's a known fact. Some of the parts that actually come to me for checking, I'm surprised when I look at the tolerances. I have a thumb rule in defining tolerances. For example, for roughing, my tolerance is always 1/5 of the stock to be left. So if my stock is about 0.5 millimeter, my tolerance will not be less than 0.1. So it will be 0.1. Or it's the other way around. If your tolerance is 0.1, then your stock to be left is 5 times the tolerance. The finishing tolerance can be between 10 to 15 microns. In some cases, it can go as high as 20 microns also. In some of the parts that I received from the customer or from my own people, I see that in finishing, people use a tolerance of 4 microns, 2 microns. It's not needed because your machine is not going to give you that accuracy anyway. When I make this statement to a customer, or when I make this statement to an engineer, that you don't have to use 2 microns for large parts or 8 microns for a large part, because you're not going to get anything less than 15, 20 microns on the machine itself. So they come up with the catalog of the machine and show me that, look, the position tolerance says it's 2 microns. The repeatability is 1 micron, so why are you telling us that you won't get that tolerance? We have to understand that the repeatability and position have got nothing to do with your surface machining. Your surface machining is something that is the accuracy of that is always generated after you cut the part, you take it to the CMM and you measure it. That is what is going to come out from your machining. And that's the profile tolerance. Generally, the machine tool makers would never come up with this tolerance because it is not something that can be decided by the machine tool vendor, because it depends on several things. It depends on your work holding, it depends on your rigidity of your machine itself, it depends on how good the tool is held, it depends on how accurate or how good the shape of the tool is. It depends on several factors. So even if you have made your tool path with 2-micron tolerance, you will never get the part in 2 microns. You will never get it, because when you're doing a sculptured surface machining or a NURBS machining, it's never 2 microns. It'll be always between 10 microns minimum and sometimes 30 to 40 microns, depending on those factors. The other very important thing I have taken into account, or I take into account, is the step over for finishing. People, I've seen customers, they have 10 diameter tool or 12 diameter tool when they use for finishing, they take very fine step over. If you look at this figure out here, and if you look at the contact point of the tool that it's making at the actual depth of cut, so if you're removing, let's say, 0.2 millimeters of cut, then you need to check where your contact of the tool is going to be. So if your step over is much less than that contact point, you're actually rubbing the tool on the part. You're not cutting it. So you will get, the surface will not be nice. So you need to find where is your contact point and what's the RPM of that particular contact point, and based on that, arrive at a step over. So it is very important that not to give fine step overs for these large parts. It doesn't make any sense, because you will only rub the tool on the part. All right, now we have seen what we have done with the computer. We've seen what needs to be done with a virtual memory. We also have seen the influence of tolerance, and how much is the tolerance that needs to be kept, what is the side step and stuff to be taken. Let's get into the software. And this is my part. You can see some yellow surfaces on the part. Now, whenever I get a part, or it's a large part, I generally will close off all these areas. Now, let me switch off those surfaces so that it's much more easier for you to look at the surfaces. Okay, so let me switch off 1, 2, 3, 4, 5, 6, 7, and these surfaces. Okay. Now this is how my part looks like. For example, I have a hole. It has got no reason to be machined in 3D, so this must be off. Right? This has to be done in drilling and then boring or drilling and reaming. Then there are two what we call as overflows, because this is a die casting die, this is an overflow. So these are overflows. Again, they are very small. Even if there's a cutter that's capable of getting inside this, it will only waste my time trying to machine this, because it's not going to finish it in any way. So why do it in my regular machining? We can do it later on with a small tool straight away. Rough it and finish it. So this particular pocket and this particular pocket need to be closed off. Right, let's come over here. There is a hole out here. Again, this has got no business. This is a simple straight hole that needs to be done later on. So I don't need to use this hole to slow down my machining. So this will be done later on for my purpose. There is a small rip out here. Again, if I'm trying to use, let's say, a 8 diameter tool, it'll try and get into this slow down my machining. Apart from slowing down the machining, these small speed breakers, what I call on the tool path, will actually cause more harm to my tool. You could have chipping. It might chip off when it's trying to get into this area. Of course, you can say I can put a radius, but still a radius is a speed breaker for me. Why do I need to get these things when I can just close them off and handle them later with only those areas, or targeting only those areas? Sometimes it's more effective to just do an EDM on this than to do milling on those, because they are deep. If you don't have a 5-axis machine, then it doesn't make sense to go into this area with a small tool. Also, I have got another small area out here, which actually again doesn't make any sense for me to keep it for machining. This needs also to be closed. So I was referring to areas that needs to be closed on my slide, and these are exactly those areas. For example, this particular rib, if I calculate the height that it needs to go, that's about 17 millimeters. And if you look at what would be the size of the tool that would be needed, probably that would be about roughly 3 millimeters. So imagine I'm taking 3 millimeters down to about 17 millimeters. So that's an L by D by about 6. Generally, L by D by 6 is actually going to give you a disastrous result with such a small tool. So all you could do probably is to take a 4 diameter tool and try and rough out as much as possible later on, local area, and then remaining we do an EDM straight away. So it is very important to identify areas that need to be closed off. And once that is done, okay, let's hide this, we don't need it. Okay, once sorry, that is done, we have closed the areas that we don't need to machine. Also, it's very important to identify which areas need local machining. For example, fillet here, because no matter what you try to do here, this fillet will not be machined exactly the way you want it to be machined. So you need to identify those areas which need local machining. The local machining need not be handled in HSM. They can be handled much better in HSS. So this portion will be done in HSS. So you need to identify these areas. Right. Once you're done with it and you're ready for machining, we can start off by deciding the strategy. There are two ways in which we can rough out this part. One is we could use iMachining, which is a quick way of scooping out material, or we could use HSR, the contour rough, and use an inserted cutter and just remove the material off. You need to toss, or you need to make some decisions here. First of all, it's very important to understand what is the height that we are talking about roughly. We are talking about 71 millimeters out here. So the maximum possible end mill that we would get for iMachining, which is economically viable, is about 16 millimeters. So if I use 16 millimeters, the best possible cutting can be between an L by D ratio of 3 and 4. So we're talking of between 48 and 50 millimeters or 55 millimeters out of holder. So for sure, we will not be able to go around to all those areas with iMachining, but we can scoop out maximum material using iMachining, provided it falls within the bracket of the tool lifetime. For example, the first tool path that we see here, if I run the HostCAD simulation, it's about 2 hours, 15 minutes. Depending on what we need to cut, a 16 diameter end mill can have a tool life anywhere between 90 minutes to 160 or 150 minutes. So we are falling within the ambit of that tool life. Plus, remember that in iMachining, your tool life actually is pushed up. So even if you take the most conservative estimate of double the tool life, so we are talking of 90 minutes and double of that, that's about 180 minutes. So we are falling within the ambit of the tool life parameter. And if you're cooling, that's, in this case, it's going to be air, it's perfect, then you could easily end up getting more than 180 minutes. So we are falling within the ambit of that tool life. If we are able to fall within the ambit of the tool life or within the limit of the tool life, it's a great idea to go ahead and cut this part or rough out this part with iMachining. However, assume if the part is pretty hard, 48, 50 HRC, then this time it will not be valid. It could go beyond 4 or 5 hours, the roughing itself. In such cases, you need to identify areas or pockets which could be handled by iMachining to cut down the time and also save on your tool life. And then remaining of that area, you need to cut using HSR. So it's a decision that the user has to make depending on size and the tool life of the particular tool that he's using. In our case, fortunately, we're getting a time of about 2 hours, 15 minutes, which is falling much inside the 180 minutes. So we're talking here of about 130 minutes. So we are very much inside the tool life limit. So it's a great idea to do iMachining, scoop out maximum material. Okay. Now we are talking of a size here. Let's calculate what's the size. We're talking of a length of about 530 and a width of about 340, and the machining height is roughly about, let's say, about 88 millimeters or 90 millimeters. So it's 540, 340 by about 90. So it's a reasonably large part. Once your iMachining is done, since you've used, in our case, we have used a 16 millimeter tool with just 50 millimeter out of holder. And we know that the deepest point on this is about 90 millimeters. It's not necessary that it will go or it will leave material, but there are chances that when it comes closer to these walls, the holder collision strategy will actually push the tool out, and it would leave a lot of material on the sides, which then needs that you machine the remaining area using an HSR rest rough strategy. So if you look at the next strategy, I have used a 16, again, a 12 corner radius 3 tool, and this is using the inserted type of tool, because here I'm not going to use the solid carbide end mills anymore. So we will use a minimum an inserted tool and outside holder value of about 55 millimeters. The minimum tool length needed to cut this part is about 65, but you can safely go between 48 to 50 millimeters when you're using an inserted tool because of the holding and because we are going with much less step down than what we would do with an iMachining tool path. Right, so once this has been done, we know that the needed tool length was 65, but it was not enough. So there could be areas where material is still remaining. So we mount another tool, same diameter, but a longer length, about 68 millimeters, reduce our parameters, even the depth of cut and side step, and generate tool paths only on those areas where my earlier tool path could not enter, or the earlier tool could not enter. So it's very important to go in stages. Okay. Now coming to the tool path itself, if I open the rest rough, look at the passes. I've kept a wall offset of 0.6. My earlier offset for iMachining 3D was about 0.5, and I'm keeping about 0.6, slightly more. The most optimum value in this would have been 0.55, but I've gone 50 microns more. I've kept about 0.6 with a step down of 1 millimeter. But the tolerance here is pretty important. The minimum tolerance that you could go with this is about 0.1. Remember my formula. 1/5 of the offset is going to be your tolerance. Also, it's very important to note here is the over thickness. What is over thickness? Over thickness is basically we are going to trim out the tool path that is having material less than 0.6 millimeter, because it doesn't make sense. For example, there are many cusps. Sometimes the cusps are just about 0.5, and the tool just touches around them and moves on them. It's a waste of motion. So what I generally do is whatever is my previous offset, to that I add the tolerance. So if my previous offset was 0.5, I add 0.1 to that offset, and that value I put over here as an over thickness. So it ends up only going into those areas where there's real material remaining to scoop out that area. Okay, this cuts down the time greatly. It cuts down the machining time as much as about 30% sometimes, depending on how much material was left out by the earlier tool. So it's very important, your wall offset, tolerance, and edit passes. So these all have the correlations. They are related to each other. Right. The same also follows for the next tool path and the edit passes. It's the same. We keep similar one. Okay. Once my roughing is done, okay, I need to sit and analyze how much material is remaining. So I could pick all of them, run the simulation. Okay, can go into Solid Verify and run quickly. Okay, I could just slow down the simulation so that you could see what has been done and run the simulation again. Right, so you can see that we've done the roughing out, and if you look, you can see there's a lot of material remaining in this area out here, especially because of the holder. So you can see a lot of material here on the wall because the holder or the tool was short, so the holder kept on moving the tool away. So there's actually a lot of material remaining on the side. So now we are using our rest rough function of HSM or HSR and scooping out that material, but going gradually down. We're using the constant Z, or the rest rough using constant Z, and gradually removing material. Even this particular tool is unable to do completely. It is still going to leave some material. Okay, so but it has scooped out a lot. Let's run the next one. Yeah, so it's removed again a lot of material. At this point, I can load my target and run a comparison between the stock left out and the final part. You can see that the material left out is more than 0.5, so we can check up by changing the maximum value to 0.8 and running the execute function. So it's between 0.2 and 0.8 most of the places. That's how the material is. At this point, it is unwise to run the finish directly because you have material that is not constant. You have got material that is more than 0.2, more than 0.8 in some cases. So you need to put a semi-finishing operation. How is that done? The semi-finishing is handled in a different way. The first principle that we use here is when you're doing a semi-finishing of such a large parts, you have to exclude the tool from going on to these near horizontal areas. Or if it has to cut horizontal, then it has to be absolute horizontal. So we have got a constant Z a tool path that shows or that is generated using a combination of constant Z and horizontal only. So if you look at the tool path, it looks something like that, wherein it's not machined most of these horizontal areas because I put a restriction on the limit angle. For constant Z, my limit angle was 20 degrees and above to be done in constant Z. Anything less than 20 degrees should not be touched. However, all those horizontal areas also need to be semi-finished. So that is done. Once this is done using the same tool, or you're using a ball nose tool, because now we are going on to our horizontal area. Using a ball nose tool, we will now tackle the linear areas. So if I use a combination of these two, if I show you, we can see that we are covering almost all of the area. How did I avoid the horizontal areas not going on this one, or the horizontal toolpath not going on this one, or the linear toolpath has not gone onto the horizontal area? If you edit the toolpath, you will see that in the passes, my angle, minimum angle I have given is about 0.01 degree. So I am asking the software not to touch something that's near horizontal or absolutely horizontal, but only machine that's something beyond 0.01. So by using this method, a ball nose tool will not waste its time going on horizontal areas. It will only go on areas that are fit for it, which fall within the angle of 0.01 degree to 20 degrees. So we are actually covering the entire part, and the same method can be used also for finishing the part. So very important that we handle or we do a semi-finishing of the entire part. Because once you do a semi-finishing, so what we'll do is, again, we will run the simulation. So I'm just going to pick all of them. This would take a minute, so you'll have to bear with me. Let's run it quickly. Switch off the holder. Now, why was it done? It was done basically, so many toolpaths, basically because for finishing, the principle is you must get as constant material as possible. It should not have uneven material. So even in spite of doing so many roughings, you will see that we have introduced another rest machining toolpath to make sure that even in the corners, the software doesn't, or the tool doesn't encounter uneven material. So we've done a lot of toolpaths before we actually hit on the finishing. This is true even if you're doing a small part, because the principle of machining is constant cutting at every point. So if you have material that's more in some areas and less in some areas, the amount of load that comes on the tool is ununiform. It's not uniform. So you will end up blunting the tool or reducing the tool life and also compromising on the surface quality. Okay. I'll just stop it when it completes about, let's say, 20–30% of finishing, so that I can show you that we have got almost constant material now for finishing. So it's very important to have constant material for finishing, especially when you're doing large parts, because you want to maximize your tool life. You don't want to stop the tool in between to check it. How is the tool behaving? So as far as possible, you need to give the tool constant material to go with, so that you actually maximize your tool life. So in short, if I had to summarize this whole webinar, machining large parts needs some tweaking on your system. You need to change some settings on your system. You need to do some internal settings for simulation. We're going to see this in the next webinar on the simulation changes that you need to make so that you can simulate large parts very quickly. We have seen, for example, in some cases with our customer that with their previous default settings, the simulation time was as high as 1 hour, and with the new settings, it was under 4 minutes. So it can make such vast difference to your simulation time. So making some changes to your system, getting first of all the right system and making those changes to the system, making internal changes to the settings of SolidCAM, and using the right tolerances, the right strategies for machining, you can actually cut big, really big parts inside SolidCAM. Okay, so this is about to be done. We'll load the CAD part, okay, and we'll do a comparison. You can see most of the areas, the color is light green, which means the amount of material left out for my finishing is about 0 to 0.2. It's between that. It's exceeding in some areas. That's because of the sharp corner existing there. But other than that, it's having already the light green color. So we have got almost near constant material. But in some areas, it still has material left out. In such cases, what I've done basically is I've introduced a rest machining cycle to remove the corners, because the tool would need near constant amount of material to cut apart. Otherwise, you will see that the tool life has gone down. So it's important to define a rest machining toolpath just before you run the finishing. It's also very important to note that the tool diameter must be the same. Whatever you plan to use for your finishing, you must use the same diameter for your rest machining before, so that you leave the same radius and you leave the same amount of material even in the corners. Right, and to end, whatever areas that you had marked for local area machining, you could machine them using HSS. This saves a great amount of time. It also improves your surface finish greatly, especially in local areas. So the summary of today's webinar is getting up your system right, especially when you're doing large parts. Remember that if you have a system, let's say with an 8 GB memory, probably it's not the right system to take to machine large parts. You could end up machining large part, but it will be frustratingly slow because the memory is not enough to handle large parts. First is getting the right system, doing the right settings for the virtual memory, doing the right settings for tolerances, using the right strategy. Like I told you in the beginning for roughing, it's smart enough to understand that you could use iMachining 3D in some area and you could use HSR in the other area, or you could use only iMachining 3D to scoop out, provided it falls in the limits of the tool life. If it doesn't fall in the limits of the tool life, then it's a smart idea to split up the area of the tool path. For example, in this case, I could do iMachining 2D and 3D only for this particular area, just to open out, because there it will be much within the limit of the tool life. It could scoop out maximum material in the most minimum time, and the remaining areas I could actually use HSR. So this decision of whether to use or where to use iMachining 3D and HSR is at the discretion of the user. So combination of the strategies, using the right toolpath parameters and tolerances, tweaking of the system in terms of virtual memory, and first getting the right system. All of these combined together can give you a much nice experience when you're doing large parts inside SolidCAM. If there are questions, I would be open to questions, and please remember that next week you'll have to join us again, because we have the second part of this webinar where I'll show you large parts with extremely fast simulation times with some tweaks inside the simulation settings. So if there are questions about what I showed today, or what I explained today of the system and the tolerances, I'm more than ready to answer